Welcome to part 3 of our lecture video series from Monday, March 13th, where we are looking at molecular orbital diagrams for homonuclear diatomics that are a little bit more complex than just our hydrogen molecule. So we're going to focus in this section specifically on homonuclear diatomics like oxygen, fluorine, and diatomic neon. And what makes this different from what we're looking at when we saw our example for hydrogen is we are now looking at linear combinations, LCs, linear combinations of not only s orbitals, but also atomic p orbitals. So let's jump right in. Let's go ahead and look at F2. So I'm going to draw my energy axis. And I am going to give myself a decent amount of space because I always run out of space when drawing my MO diagrams. And there's my energy axis. Okay, we're going to start by placing our atoms that are making our molecule kind of to the left and to the right in this diagram, with the molecule to be made in the center so that we can show what atomic orbitals are combining to form now our new molecular orbitals. And I like to draw out the entire electron configuration for each of my elements that are coming together in a molecular orbital diagram. So for fluorine, that is 1s2, 2s2, 2p5. 1s2, 2s2, 2p5. So first up, it looks like we have to look at combinations of the 1s atomic orbital on each fluorine. So let's look at the combinations that result from a 1s and a 1s coming together. So S and S. This is very similar to what we saw in hydrogen. We will see the additive combination to give us our sigma sub s bonding orbital, and the subtractive combination or destructive combination coming together to give us our sigma s star anti-bonding orbital. Where again, this is our lower energy molecular orbital, and this is our higher energy molecular orbital. So I'm going to create from my 1s's, and I think I'm going to go ahead and draw them as well as write them out. So from each of my atomic 1s's, I'm going to form now a sigma s bonding orbital and a sigma s star anti-bonding orbital. And I would like for you to know the shapes of these molecular orbitals. Okay, using a dashed line to show what molecular orbitals were formed from which atomic orbitals, I can now fill in each of my atomic orbitals with their initial respective electron count. So that was 1s, 1, 2 in each of our fluorine atoms. And I'm going to go ahead and wait to fill in my electrons until I keep building my molecular orbitals. So I'm going to wait till the end to fill things in. Okay, 2s. Very similar to what we see with the 1s. I can already tell I'm going to run out of room. I'm just going to move this down. So let's look at the 2s. The only difference is now our atomic orbitals are higher in energy than the 1s, right? N equals 2 instead of N equals 1. And just like before, since I know that I'm looking at combinations of s-type orbitals, I'm going to create a sigma sub s bonding orbital. and a sigma sub s star anti-bonding orbital. And if you want to sketch this out, 2s, 2s, creating our 2 sigma and 2 sigma star. No, I wanted a highlighter. There we go. Molecular orbitals. Okay. And then if I go back to my electron configuration, each of my fluorine atoms contains 2 2s electrons. So just like my 1s, I'm going to fill them and then connect. So I'm showing what atomic orbitals are responsible for the formation of which molecular orbitals. And I am obviously very bad at drawing dashed lines, so hopefully this color coding helps. Okay. And again, because I know myself, I'm gonna try to maybe make this a little bigger, like so. Okay. Now it is time for us to look at our, let's see here. Let's do our p orbitals. And this is where things get interesting. So remember, our p orbitals combine in a couple of different ways. We can have both a head-on combination with a p orbital, as well as our side-on combination, meaning we can form both sigma type and pi type molecular orbitals. So I'm going to, let's see here. Let's look at the sigma type. So this is a head-on combination of our px orbitals, the ones that are oriented side to side. And if this highlighter is hard to see on your screen, hopefully this helps. Okay, so in the additive combination, we form a sigma p orbital, which looks kind of like this. Again, get an outline for definition. Something like this. So this is our sigma p bonding orbital, where we get then here for our anti-addition, something that looks kind of like this. Oh, no, I think I'm going ahead. Something like this. There we go. And this gives us our sigma p anti-bonding orbital. And this is all from our head-on combination. Now we also have our side-on, so I'm going to continue that down on the next page. So we've got the side-on combinations for both our py up-down and our pz in-out. And these give us the same style of combinations or same shape of molecular orbitals, just rotated in 3D space. But let's look at them all anyway. Okay, so for our bonding MO, we see something like this. This is our pi px MO. And then for our pi py, we get this shape. Where we have our two planar nodes. And I could draw the same shapes here for my PZ. So it's just same as my PY, but rotated in 3D space. So this is sticking in and out of the screen. And for the anti or subtractive or interference combination, something like this. Ooh, no, don't want to erase that. Where we have our two planar nodes, which creates our pi pz star. So because we have two orbitals, the py and the pz, that come together in a side-on addition, we generate now 4 molecular orbitals, 2 bonding and 2 antibonding. So how on earth would I structure this? So it turns out that the bonding is lower in energy for the antibonding. And we have this kind of symmetry in how the antibondings are going to be organized. So it's always going to go sigma and then pi star, sigma star. So let's look at that. So I'm going to show in orange now, I've got my 3 2p orbitals. And I'm going to do X, Y, Z. We'll see if we can use dashes to make this visible. And I think I'm going to need to move these up a little bit just to give myself some space. Okay. So the lowest energy MO that's going to be formed is going to be my sigma p bonding orbital. Followed by my pi p, meaning my pi px, pi py, pi pz bonding orbitals, followed by my pi star antibonding, with the highest being then my sigma p antibonding. Okay, so I am being a little vague here with my dashed lines because otherwise I think it would get kind of messy. But we know that the sigma p bonding and antibonding orbitals come from combinations of my head-on or px orbitals combining. And then the pi orbitals come from the side-on combinations. Okay, and then in each fluorine atom, 2p5, so we've got 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, so now I need to start filling in my electrons. So starting down here, I've got 2 1s electrons from one fluorine, 2 from another. That's a total of 4 electrons. Filling from low to high gives me 1 pair 2, 3 pair 4. Looking at now my 2s, again, I have 2 electrons in the 2s orbitals from each of my fluorine atoms, giving me 4 total electrons to fill in my molecular orbitals with. So 1, then 2 in the sigma s, and then 3 and 4 in my sigma s star. And now looking at our p orbitals, We have 5 p electrons in each of our 2p orbitals from each of our fluorine atoms. So that makes a 10 total electron count that has to be filled here. So I'm going to fill load high, 1, then 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I were to then look at my MO diagram for fluorine, it would be everything encapsulated in these diagrams here. Okay, so if I want to describe what's going on here, as a result of my 1s combination, I have 2 electrons in my sigma s bonding and 2 electrons in my sigma s anti-bonding. Same deal here for my 2s. I have 2 electrons in my sigma s bonding and 2 electrons in my sigma s star anti-bonding. Okay, looking here now at my p orbitals, I have 2 electrons in my sigma p bonding and 4 total electrons in my pi p bonding orbitals. And then I also have these electrons up here. So then I have 4 electrons total in the pi p anti-bonding orbitals. And this is what the molecular orbital diagram looks like for fluorine. Now, I think I want to switch up our lecture. So instead of talking about sp mixing quite yet, I think I want to do bond order and molecular stability first, because I want us to be able to understand like the point of looking at MO diagrams this way. So let's do bond order and molecular stability next. And then we'll look at physical properties like para and diamagnetism. And then we'll talk about a phenomenon called sp mixing, if we have time. Okay, so I will see you in our next video, video 4, where we discuss kind of the results of an MO diagram like this one for fluorine.